In the autumn of 1923, Germany's state railway began feeding an empire of timetables, forms, and technical drawings into filing cabinets built around one strangely proportioned sheet of paper. The shape that repeats. In the autumn of 1923, Germany's state railway began feeding an empire of timetables, forms, and technical drawings into filing cabinets built around one strangely proportioned sheet of paper. The railways were among the largest organizations in Europe. Their clerks had to coordinate stations, freight depots, workshops, payrolls, and thousands of kilometers of track. A mismatched form was not merely untidy. It could waste storage, complicate copying, and make information harder to move through a machine whose fuel was paper. The sheet they adopted is now so ordinary that it almost disappears in the hand. It is 210 mm wide and 297 mm tall. We call it A4. Its dimensions sound arbitrary, as though they were selected by a committee with a ruler and a fondness for awkward numbers. But hidden inside them is an elegant trick. Divide the longer side by the shorter and the answer is close to the square root of 2. Cut the page in half across its longer side, and each half has the same proportions as the original. Enlarge one of those halves by a precise factor, and it fills the original sheet without a changed margin or a cropped edge. That repeating shape is the hinge of this story. It linked a physicist's observation in 18th century Göttingen to a German industrial standard, then to printers, folders, envelopes, cabinets, photocopiers, passports of bureaucracy, and the documents of international organizations. A4 did not conquer the world because it was beautiful, though some thought it was. It spread because it made paper behave like a system. A letter from Göttingen. On October 25, 1786, George Christoph Lichtenberg wrote from Göttingen to his colleague Johann Beckmann. Lichtenberg was a professor of experimental physics, an aphorist, and a sharp observer of everyday absurdities. In the letter he discussed a question that sounds almost comically small: what shape should a sheet of paper be? His answer depended on a rectangle whose sides were in the ratio 1 to the square root of 2. The mathematics is simple enough to do on a desk. Suppose the short side is 1 and the long side is x, have the rectangle across the long direction. Turn the half sheet sideways. For its proportions to match the original, x must equal 2 divided by x. Therefore x squared equals 2, and x equals the square root of 2. The ratio is irrational, but its practical effect is wonderfully tidy. Every halving produces a smaller version of the same shape. Lichtenberg did not invent the square root of 2, of course, nor did his letter immediately establish a paper standard. He even noted that paper with approximately this proportion could already be found. His contribution was to recognize and explain the format's peculiar advantage: a book page made by folding the sheet would retain the shape of the sheet itself. Images and text could move between sizes without being recomposed into a fatter or thinner frame. 12 years later, revolutionary France produced a curious echo. On November 3, 1798, or 13 Brumaire in year 7 of the revolutionary calendar, the government published a law concerning stamp duties on paper. Its named formats included dimensions corresponding closely to later A2, A3, B3, B4, and B5 sizes. The law was a tax measure, not the birth certificate of modern A4, and that French system did not become a lasting international regime. Still, it showed that metric dimensions and self-similar paper sizes had entered practical administration long before office printers existed. The idea appeared, vanished from general view, and waited for industrial bureaucracy to make it urgent. The engineer and the square meter. By the early 20th century, the problem was no longer philosophical. Offices and factories consumed forests of forms. Printers, binders, stationers, architects, and government departments inherited a jumble of formats. A document might fit one folder but not another. Reducing a drawing could leave wasteful borders. Stocking many nearly similar sizes tied up money and shelf space. Standardization promised savings, but only if everyone accepted the same answer. German chemist Wilhelm Ostwald promoted a square root of 2 world format in 1911. His proposal helped revive the geometric principle, but its chosen base dimensions did not become the final system. The decisive refinement came from Walter Postmann, a German engineer and standardizer. Postmann combined the repeating ratio with a metric anchor that was easy to understand, the A0 sheet would have an area of exactly 1 square meter. A rectangle with that area and the square root of 2 proportion has theoretical sides of about 841 by 1189 millimeters after rounding. Have it and you get a 1. Have a 1 and you get a 2, then a 3, then a 4. For havings turn 1 square meter into 16 A4 sheets, each measuring 210 by 297 millimeters within the standard's rounding rules. The names are not a ranking of importance. They are a family tree. The number tells you how many generations of havings separate a sheet from A0. On August 18, 1922, the German standards body published DIN 476, trimmed sizes of paper. It set out the A series and related formats. This was not Postman issuing a decree by himself. DIN describes the standard as adopted by consensus among interested parties. That detail matters. Standards gain power through coordination. A size becomes valuable when the paper mill, printing press, office supplier, filing cabinet maker, and customer all expect it. The German State Railway Directorate became the first institutional adopter in the autumn of 1923. Railways were an ideal demonstration. They operated at national scale, generated standardized information, and depended upon documents traveling between distant offices. If one paper family could serve a postcard-sized notice, an office letter, and a large technical drawing, then storage and reproduction became easier across the network. A geometric curiosity had found the bureaucracy big enough to reward it. How a page builds a room. The great advantage of the A series is not simply that A4 fits a printer. Printers were built to fit A4 because organizations had already committed to the system. Once adopted, the sheet began dictating the world around it. DIN notes its influence on filing trays, binders, sleeves, desk drawers, cupboard dimensions, and envelopes. The page became a quiet unit of architecture. Imagine an engineering drawing on A1. Reduce it to 71% in each direction and it fits A2, reduce again and it fits A3. Because area changes with the square of linear scale, that familiar copier setting near 71% halves the area while preserving the frame. Going the other way, roughly 141% doubles the area and advances one step up the series. A chart can move from handout to wall display with its composition intact. Two A4 pages can be placed side by side on A3. A folded A3 becomes an A4-sized item. These are small conveniences individually. Repeated across millions of documents, they become infrastructure. The system also separated useful jobs among related families. A sizes served finished documents. B sizes supplied intermediate formats and larger printed matter. C series envelopes were designed around A series contents. A C4 envelope accepts an unfolded A4 sheet, while folding A4 once produces A5, suitable for a C5 envelope. The exact standards evolved, and ISO 269 for envelopes was later withdrawn, but the design logic remains visible in stationery shops. The contents and their container belong to coordinated geometric families. Other countries adopted the German model over the following decades. International standardization arrived in 1975 with ISO 216, derived from the DIN system. The current edition, ISO 216:2007, specifies trimmed A and B series sizes for administrative, commercial, and technical use, including forms and catalogs. It does not claim jurisdiction over every newspaper, book, or poster. Nor is A4 literally universal. The United States and Canada remain strongly attached to letter paper, whose 8.5 by 11-inch proportions do not survive halving. Worldwide here means an international norm used across most of the world, not every desk without exception. The geometry inside the machine. It is tempting to tell this as the triumph of a perfect idea. History was Messier. Lichtenberg explained the ratio. Revolutionary France briefly encoded related metric sizes. Ostwald campaigned for a world format. Postman designed the practical series. A standards committee approved it, and a railway proved it at scale. Adoption took decades. Each participant supplied a different part: observation, administration, advocacy, engineering, agreement, and use. Yet the result feels almost magical because the standard hides its complexity. Pick up A4 and you hold 1/16 of a square meter, shaped so that its descendants resemble it. Fold it once and the new rectangle is not merely smaller. It is geometrically the same. That fact means a printer can impose two reduced pages on one sheet, a copier can enlarge a page without redesigning it, a cabinet maker can anticipate the folders, an envelope maker can anticipate the letter, and an international office can exchange a document knowing what physical frame the recipient expects. The page even demonstrates the difference between invention and standardization. No one needed permission to cut a square root of 2 rectangle before 1922. The valuable act was persuading an ecosystem to use the same rectangle. A standard is a collective promise about the future. When enough people keep it, manufacturers can build machines and furniture around it, and users stop noticing the promise at all. The absence of friction looks like nature. So the next time a copier offers 71%, or 2 portrait pages sit perfectly on one landscape sheet, remember the chain behind that button. It leads past the railway clerks of 1923, past Walter Porcman's 1 square meter ancestor, to a letter written in Göttingen in 1786 about the pleasing shape of folded paper. The genuinely surprising connection is this: much of the modern office, from the zoom ratios in its machines to the depth of its drawers, is organized around an irrational number. The square root of 2, a number that can never be written out exactly, gave the paper world a shape it could repeat forever. \n before standardization, paper size was not a neutral detail. Handmade sheets inherited the dimensions of local molds, while printers described books by folds such as folio, quarto, and octavo. Those names explained production but did not guarantee one universal finished page. Industrial papermaking increased supply, it did not automatically erase regional conventions. Then typewriters, duplicating machines, blueprints, and mass administration turned every sheet into one link in a production chain. Its dimensions determined how blanks were cut from stock, which press could accept them, how efficiently they traveled, and which cabinet could store the record afterward. \n. There was an economic elegance in the new numbering too. A printer could begin with a large A-series sheet and cut downward. Each cut created 2 sheets of the next size, always in the familiar proportion. Real printing still required allowances for trimming, press grips, and bleed, so the system did not abolish waste. It did make planning more predictable. A designer could adapt the same composition for a memorandum, booklet, or poster without inventing a new rectangle. The standard dictated none of the words or images. It standardized the blank space beneath them, and that made the blank space interoperable.